So next I'm really taking a very special pleasure to introduce the next speaker, John Urschel. First of all, I'm happy to say that John is a Penn Stater, alumni, and he actually got the bachelor and the master degree from Penn State about, I think, 6 years ago. As you can see how muscular John is, he's a professional football player. He played with Penn State when he was a student here. And then he was drafted by Baltimore Ravens to become a professional football player. I think it's an offensive lineman. And for 3 seasons later, John made a big decision. And he also made a lot of headlines in the news to retire from a professional football player to become a professional mathematician. John, I think you made a wise decision, okay? And I'm also very happy to mention that I had the pleasure to have John taking some of my classes that I taught at Penn State. I also had the pleasure to have advised his master thesis. And I think, John, I actually read from the news. You had a perfect GPA scores, and that's remarkable. Certainly, John is really the best student I taught since I've been here for quite a long time, 30-some plus years. And John, as I didn't make, after this football retirement, he went to MIT to pursue a PhD degree, the math department. I think he's finishing up this year. I heard that John is now sitting on many job offers from universities like I think like Harvard, MIT, Princeton, Stanford, Berkeley, Cornell, NYU, all this top university. I think, John, you're going to have another tough decision to make where you would go next. But anyway, John, I just want to say a few things about John's research. And he's, starting from numerical analysis when he was a graduate student here, a student here. And now he's doing graph theory, data science, machine learning. Even though he's still like a graduate student and also the busy schedule as a football player, he has already published many great papers, solved several difficult mathematical problems. For example, I think the paper John published in the Science Journal of Numerical Analysis as a sole author. He obtained some groundbreaking results on sinusoidal binaural tessellations and solved a long-standing problem regarding the computation of such a tessellation. Most recently, I heard that John obtained a solution of a symptomatic version of a two decades old conjecture in spectral graph theorem. And really, difficult to keep track of all this many wonderful work you're doing. But today, John is going to talk about his work on stress minimization for low diameter graphs. John, please.
Yeah, Jin Chao, first of all, thank you for having me. I have to say that it's a great honor to be back and to be able to give a talk, virtually at Penn State. Jin Chao was my master's thesis advisor, and I can say that Jin Chao is sort of clearly the person who really drove me towards where my research is now. Before I met Jin Chao, I was actually working in dynamical systems. I was more of a pure mathematician, and Jin Chao introduced me to numerical analysis. And in fact, my first introduction to sort of graph theoretic problems as they relate to computation was through a project that Jin Chao recommended for me. And so my current research as it stands, really grew out of that project and also the coursework that I took from Jin Chao. Today, what I would like to talk about is an interesting optimization problem. And here I'll just leave up the following slide while I just give a brief introduction. I want to consider an optimization problem in which we're given some graph, or we can think about this as some set of data points in Euclidean space, which in some ways can be encoded via some weighted graph. And we want to try to look at the problem of embedding this into a low-dimensional Euclidean space, often embedding this in the plane or embedding this in R3. And this is something that has proven to be a very useful task in data science, to be able to visualize what a given data set looks like sort of fundamentally. And this does have some mild connections to some of the things Ingrid talked about. Of course, Ingrid talked about things related to diffusion mapping, which is something very close to my heart as a spectral graph theory person. But what I'd like to focus on is something called stress minimization, where what we have is we have an optimization problem in which we have some distances between, let's say, n objects, and we would like to embed these n objects into RD. Imagine D is maybe 2 or 3. And we'd like to embed them so that the distance between the location of 2 objects, let's say in the plane, is close to their distance given by our distance matrix. And this minimization problem is an example of a sort of broader class of sort of data visualization techniques called force-directed layouts. This very much started with Hutt's spring embedding theorem, Eads algorithm, then a number of heuristics for stress minimization, and very recently this very popular UMAP algorithm. And I'll briefly review the some of the literature around force-directed layouts. And there's a lot of different heuristics over the years to approximately solve this optimization problem. But the one thing that you don't see much of is strong theoretical results. Questions about algorithms to approximately solve this optimization problem, let's say, with some provable guarantees. Or also any sorts of algorithmic lower bounds that tell us something about the best we can do for this problem. And I think this is an important perspective to take. There's always power and usefulness in strong heuristics to solve problems in practice, but I find that trying to understand what's going on theoretically with the problem really helps you understand why these heuristics work, when they don't, and it often gives you an insight into how you might make a slightly better algorithm. Okay. And so a brief sketch of what I'll talk about today. First, I'm going to introduce sort of the broad class of force-directed layouts so you can see where the stress minimization problem fits in the timeline of sort of popular force-directed problems. Then I'm going to briefly review some of the very popular heuristics for stress minimization, many of which are sort of coded as data visualization packages, which you can use in R and a number of different programs. Commodore Kawaii and the Smock-Off algorithm are extremely popular. The concept of using a variant of stochastic gradient descent is much more recent. And then in part 3, I'm going to look at a lot of different theoretical guarantees for this problem, which is work of mine joint with Fred Kohler at MIT, who is also a PhD student who focuses on machine learning, and Eric Domain, who is a sort of very well-known professor in computer science who focuses on a number of different topics, including graph drawing. And when we look at these theoretical guarantees, we're going to give a sketch of an algorithmic lower bound for this problem, and then we're going to produce a very natural type of algorithm with strong provable guarantees and take a look at a couple experiments to see how this performs. Okay. So first, as an introduction to force-directed layouts, it's more or less widely agreed that this sort of hallmark first example of what is called a force-directed layout, which you can imagine is some sort of drawing of some vertices with edges where you have certain interactions and certain repulsive forces in some sense. It's a very broad class, but This first theorem is very much a pure graph theory result from, I believe, the 1960 or so. And what Hutt's embedding theorem tells us is if we have some three connected planar graph, which you can think of as, let's say, the skeleton of some convex polytope, or you can think of this as, let's say, some finite element mesh, which has reasonable properties of connectivity. If you pick some face of your graph and you embed this in the plane as a convex polygon, and then all you need to do is just state that every other vertex of your graph is placed at the mass center of its neighbors, then this embedding is planar. It's uniquely determined by the embedding of the outer face. And so in this drawing I have here, here's a planar three connected graph. We choose a face which consists of four vertices. We just make a square here, and placing every other vertex at the mass center of its neighbors results in a very nice embedding. Okay, so this is more or less like the original result. Between Tutt-Spring embedding theorem and this stress objective function, a number of different techniques were considered. Eads considered a very natural algorithm in which you had attraction along between vertices and repulsion and edges, but there's a number of different models that can be used here. And the stress minimization function, which I showed you on the previous slide, is a very, very natural and sort of intuitive way to think about this. We have n objects. They're some distance from each other. Let's suppose this satisfies triangle inequality. And we're given some dimension. And we just want to minimize this energy, this objective function, for some fixed choice of weights. And experimental results, which have to do with how nice a embedding looks, has shown that the best choice of weight is actually 1 over distance squared. And that is what we will be looking at and using in this talk. And this has a very natural force-based interpretation. Suppose we have some graph on n vertices and we want to embed this into RD to minimize the stress objective function here, where I've set this weight to be its typical value. This just corresponds to a physical situation where particles I and j are connected by a spring with equilibrium length equal to their graph distance. And this follows Hooke's law with a spring constant of 1 over their distance squared. So this is a very natural interpretation for this setting. And much more recently, there's the very popular UMAP algorithm, which is a data visualization alternative to t-SNE, which, given some data set, what this algorithm does is it constructs a weighted graph and it performs some type of force-directed layout. This particular example is quite complicated. The objective function is pretty complicated with repulsion between vertices and attraction along edges. And this also, as you would expect, has a non-convex objective and uses a heuristic to reach a local minimum. Okay. Now I'll just briefly cover some of the popular heuristics for this stress minimization problem, which is really the focus of our attention today. So first is this so-called Kawaii algorithm. This is a heuristic which iteratively minimizes the objective in the plane. And what it does is it just iteratively chooses a different vertex, and at each step, it tries to minimize the energy function with respect to that vertex. This is just a sort of iterative greedy approach. The way in which the next vertex is chosen is based off the one that maximizes this quantity here. And on the right-hand side, you can see some images from their original 1990 paper in which they draw a number of different graphs in the plane using their algorithm to minimize the stress objective, and they get these quite beautiful results. In the top left, you see a cube. The top right, you see this sort of triangle which has been subdivided. The bottom left is this beautiful symmetric graph. And the bottom right, I believe, yes, I think that's a dodecahedron. And it just looks very, very aesthetically pleasing, I would say. Since the Kawaii algorithm, an alternative technique which has been proposed is the Smock-Off algorithm, which the basic idea of this heuristic is that our energy function can be written as a constant plus these sort of two terms, where this first term is very easy to deal with because we have this norm squared, which has nice properties. It's very easy to sort of optimize over. What makes this problem difficult is actually this term at the end. And one way to try to deal with this issue is to take our stress function and upper bound it by a quadratic function, not in n variables representing the n locations of our n objects, but two n variables, where we can imagine the first n represent the location of our objects, and you can think the last n represent previous locations, where this upper bound satisfies nice properties where when the previous locations and the current locations are equal, this actually equals the energy. And simply performing alternating minimization on this function can be shown to decrease stress at each iteration, thus leading to a local minimum. Most recently, stochastic gradient descent, a version of this, has been proposed to approximately minimize this problem. And in fact, in this work by Zhang, Pawar, and Goodman, they found that a version of stochastic gradient descent actually performs best. And this sort of algorithm which they give, unlike the previous two, there's no equation solver, no Newton's method, no intelligent initialization, but yet somehow you get high quality and strong results. And on the right-hand side here, it's just some visualization of some graphs which they drew using their algorithm. And these graphs are some of these I recognize as pretty typical benchmarks from, let's say, like the sparse matrix collection. Okay. What I'd like to focus on today is looking at this objective function and attempting to understand what we can say about this problem theoretically. There are a great deal of heuristics in the literature that take different approaches and really try to output good local minima reasonably quickly. But I think it's important to try to understand if we can get a high quality approximate solution with theoretical guarantees and what barriers there may be. And so the first thing I'd like to focus on is the barriers. And to show the barriers that exist, I'd like to give you a sketch of what is a very, very, in my opinion, a very, very sort of nice, sort of slick hardness proof. And so what I'd like to do is consider our stress objective function, but I'd like to consider a specific subcase of it. So I'd like to restrict ourselves to 1D just for simplicity. What I'm going to show you, what follows actually holds for any dimension D, but I think 1D is simplest to show. And I'd like to consider a specific case where we consider a weighted stress objective for some fixed undirected graph G. And you imagine these weights map each vertex to the set of natural numbers. You can imagine this is like having a data set in which you can have multiple copies of points, but here I'm making the restriction that all points are some sort of like integer value away from each other. And this sort of data set can be represented as a graph. And so for this more specific subproblem, the more specific you can sort of prove this for hardness, somehow the stronger this is. And I'd like to sketch an algorithmic lower bound for this subproblem. And so what I'd like to do is sketch a proof that this weighted version, this decision problem where I give you a graph, I give you a weight function that maps my vertices to natural numbers, and I input a constant L, and I want you to output true if there is some function such that my energy is less than or equal to L, or false otherwise. And I want to show that this is NP hard. And to do this, I'm going to show that if I can solve this problem, this means I can solve max all equal 3 set, which I will define in a second. Okay. So what is this max all equal 3 set? So suppose I have n variables, x1 through xn, which can take value, let's say 0 or 1. These n variables correspond to 2 times n literals. So for each variable, we can consider the variable itself or its negation. I'm going to take m clauses, C1 through Cm, where each clause consists of a set of exactly 3 of these literals. And this max all equal 3 sat problem, what it tries to do is it attempts to find some assignment of the variables x1 through xn equals to 0 or 1, or you can imagine true or false. And it wants to maximize the number of clauses that has all of its literals equal to each other. Namely, all 3 of its literals are either all true or all 3 are all false. It's important that we consider the max version of this because it's a fairly straightforward exercise to see why removing the max somehow sort of gets rid of the hardness. I think that's fairly straightforward to see. But for people who aren't so familiar with this problem, I'd like to give a quick example. Suppose we have variables x1, x2, x3, and we have the following 4 clauses. One thing that you'll note is that if we just set x1 equal to x2 equals to x4 equal to 1 and x3 equal to 0, then clause 1 is satisfied because all 3 of these literals are true. Clause 2 is satisfied because all 3 of these literals are false. But clause 3 and clause 4, neither of these are satisfied. And you can tell that these are the best we can do, as C1 and C3 both having this all equal property is mutually exclusive, and the same for C2 and C4. Okay, and so I'd like to give you a sketch of a very slick reduction. So given some instance of max all equal 3 sat, what I'd like to do is construct a stress minimization problem, which if I solve it, I will manage to have solved max all equal 3 sat. And so what I'm going to do is I'm going to build a graph where I have a vertex for every literal, I have a vertex for every clause, and I have one other vertex. And what you can imagine is I have a very heavy weight on my one extra vertex and a much lighter weight on all my other vertices. What I'm going to have here is every literal is going to be connected to this very large vertex. Clauses will be connected to the literals they contain. And then also literals which are not negations of each other will be connected. And so what this leads to, without loss of generality, if this very large vertex is set at the origin, it leads to a situation in which the weight at our sort of this extra vertex is so large that all of the other vertices have to be almost their correct distance from it. And so this means that all of our literals are either at +1 or -1, and all of our clauses must be at +2 or -2. Like I mentioned before, variables and negations are at graph distance 2 because all others are at graph distance 1. Okay, and so we roughly know that we need to satisfy this condition that a literal and its negation need to be on opposite sides. And you can already start to see how we're solving max all equal through this graph drawing problem. Because clauses are connected to their literals in distance 2 from others, clauses always want to be on the same side as the majority of their literals. And this means that, roughly speaking, the energy of this embedding, or the energy of this drawing rather, depends on how many clauses are on the same side as all 3 of its literals, which means that the energy of the drawing of this graph is intimately connected to the solution to the max all equal 3 sat problem. And this gives us a sort of theoretical algorithmic lower bound that solving this decision problem exactly is NP hard. Now, the question, given this information, is, okay, yes, we see we have a hardness proof here, but you'll note from the reduction, we really needed to make use of some sort of stabilization. The stabilization in the form of this extra vertex, which has quite a heavy weight. And the natural question you might ask is, well, in that case, can you tell me something about, let's say, approximation algorithms? Is there a polynomial time approximation scheme? For instance, suppose we were able to show a polynomial time approximation scheme, then this would tell us that, yes, this hardness result is good, and you really can't say much more. You can't really show something like APX hardness, okay? And so in order to prove some sort of approximation guarantees for an algorithm, we need some sort of structural results about optimal embeddings. And so the first thing that we should note is that for the stress minimization problem, and I'm not going to sort of go through details, but one intuitive thing that you would expect that does indeed hold is that, suppose I give you a graph and it has diameter, let's say D. It would be pretty intuitive, and you would expect that if you embedded this graph optimally into a low dimensional Euclidean space, the largest distance between the embedded points would be at most, let's say, of order D. And in fact, although you can't say something that strong using very basic methods, I should say that by even just using simple first order conditions, you can show that there's an embedding that lies within, let's say, D squared plus D. And you can obtain stronger results with more work, but I think it's best if I just show this because this is sufficient for what follows. Okay. And one other structural result, which I'm not going to write here and I'm not going to detail too much, is that, as you might expect, if you have a graph with a low diameter, then this implies that you can lower bound the energy of the optimal embedding. And this will be important later, because what I'm about to show you amounts to an algorithm which obtains additive approximation. And a natural question which may come up is, how can this additive approximation be converted to a multiplicative one, if it can at all? In the sense that, of course, polynomial time approximation schemes aim for a multiplicative approximation. And so that really is a key structural result, which will take the additive results, which I'm about to show you, and show that these can be framed as multiplicative results for low diameter graphs. Okay. So the main workhorse that we're going to require to be able to whip up a very sort of quick and natural looking algorithm with theoretical guarantees is to make use of a very simple greedy algorithm for max constrained satisfaction problems. So there's a very simple greedy approach proposed in 2008 in which what this algorithm does, given some constrained satisfaction problem, which you can imagine is just looking at some objective function, I'm trying to highlight, but some objective function of this objective function in the middle and trying to maximize this. And all this greedy algorithm does is it picks some small number of indices to initialize, and it just looks over every single possible assignment of these initial vertices or variables in a given alphabet. And then after it looks over each initial guess of these, let's say first 3 or 5 or 10, then what it does is it chooses each other variable as the one that locally maximizes the objective function. Okay. And this greedy algorithm for max constrained satisfaction problems does have strong theoretical guarantees. So suppose you have some alphabet and we have these functions Fij, which map from pairs of indices in our alphabet to some interval of bounded size. then what this algorithm can provably do is for any epsilon greater than 0, for an initial number of brute force vertices of the order 1 over epsilon squared, runs in time, let's say n squared times the size of the alphabet up to order 1 over epsilon squared, and returns n values for x1 to xn such that the expectation of the output we get is within, let's say, epsilon times mn squared for any other value in our alphabet. So it's within this additive factor of optimal. And the reason why this is so nice is because if we wanted to compute the maximizer using brute force, this would be time like the size of our alphabet to the power n. It'd be exponentially slower. One quick small detail is, yes, what I showed you was an expectation, but this can always be converted to a high probability guarantee using just, let's say, Markov's inequality and just repeating the algorithm. There are deterministic algorithms with similar guarantees, but these are much more complicated, and I think this is a simple one and one that's also easily implementable. Using these, this greedy CSP algorithm, obviously we'll be using this for a minimization problem instead of a maximization problem. And so that's one thing I want us to keep in mind. And so you can just negate all of these Fijs. And of course, our Fij is just going to be the interaction between vertex I and vertex J with respect to our energy. But what we need to be able to apply these types of max CSP algorithms is, first of all, we need some sort of bound on the interval that these functions are mapping to, which I gave you in the form of sort of a ball in which some optimal embedding lies in. We just need to produce fairly straightforward Lipschitz constants for these functions, which can, these lemmas are sort of very, very basic calculus. You can show that the type of functions which we're dealing with for our stress minimization objective, these have very straightforward, nice Lipschitz properties. Using that paired with a standard sort of error estimate for an epsilon net from Verschinen, this is sort of like the standard typical reference, which sort of tells you that if you pick some number of points and you put this, let's say, on some points in some ball, you can always find some point within, let's say, epsilon if the number of points you choose is at least, let's say, 3r over epsilon to the power d, where r is the radius of your ball and d is your dimension in Euclidean space. And just pairing these two sort of very straightforward things, you can actually immediately get out a reasonable approximation guarantee between the optimal solution of the constrained satisfaction problem, which you can imagine we're moving towards, and the optimal solution of our problem in general. So this is sort of looking at the error loss due to discretization, and we see that this is roughly of the order like 4 times epsilon rn squared, so not too bad. Okay. And from this leads to a very, very natural approach to try to approximately minimize our objective function with strong provable guarantees. It's all we attempt to do is we build some epsilon net of a ball which contains a optimal sort of solution. We apply a greedy CSP algorithm. In particular, we can just apply the one which I showed you. And we just approximately minimize this discrete version of our problem. And then we just return the solution. And from the theoretical results and the tools which I showed you, this leads to an additive, let's say, epsilon n squared error in runtime, which is polynomial in n. In fact, it's quadratic in n. Okay.
We'll go stock.
Jin Chao, do you have a comment? What did you say? Okay, I'll continue on. I think I heard Jin Chao say something, but I'll keep going. Okay, the proof of this is fairly straightforward. We just sort of look at the error due to both of these components. And from there, I should note that you can convert the runtime of this algorithm to something which is n squared plus a factor that only depends on sort of the diameter, dimension, and your choice of epsilon, but this leads to sort of a more complex greedy algorithm. These results in expectation can always be converted to high probability just by repetition and Markov, like I mentioned. And like I was saying before, yes, these are additive errors, and this is an additive approximation, but because there are structural results which we proved to give lower bounds on the energy of, let's say, a low diameter graph, these additive approximations can be converted into multiplicative ones. And so this is indeed a true, let's say, polynomial time approximation scheme for, let's say, a class of low diameter graphs, which you should note is actually the exact type of framework which we use to show our hardness. And so this is like nearly matching in some sense. I'd like to briefly show you all a couple of experiments where we look at a couple small examples and we just see how this sort of behaves. We take, this is just a Watt-Strogatz graph. We look at embedding this graph using stochastic gradient descent. We look at this using our greedy algorithm, and we see that stochastic gradient descent really does perform well in practice. And in fact, using our greedy algorithm paired with stochastic gradient descent, which has sort of the provable guarantees of our problem and then some, plus the sort of strength of the stochastic gradient descent heuristic, tends to outperform just both by themselves in practice. Here's another graph in which you sort of see the same behavior. And for this last one here, we have a 3-community stochastic block model. And we look and we see that indeed this greedy plus gradient descent again sort of does perform best. And we see this over and over again. And this leads to some very natural questions moving forward. For instance, given how well gradient descent type techniques perform just with random restarts, it begs the question, does this type of approach have a similar guarantee? Because this gradient-based type optimization seems to find high quality minima, even though this objective function we have is highly non-convex. And in fact, by using a different variant of a greedy CSP algorithm without an initial brute force step, you can actually still achieve an additive, let's say, order epsilon times n squared approximation, which without the initial brute force step is starting to seem more and more like gradient descent. And so a real interesting question is, does there exist a similar guarantee for this gradient descent, which is in some sense kind of a greedy procedure? This is somehow quite plausible and also sort of interesting. And so these are very interesting questions moving forward for the stress minimization problem. The other interesting question, I would say, is trying to better understand more complex or more sort of involved objective functions like that of, let's say, UMAP. And so these, I believe, are sort of very interesting and important questions for sort of understanding data visualization, sort of as machine learning and sort of data science moves forward. I'd like to say thank you to Jin Chao and the Penn State Math Department for having me. The results which I talked about should be on archive in the next week or two. I can say that this is just sort of one area of my research interests. I also have a lot of interests related to machine learning, things like determinantal point processes. I also am quite interested in Voronoi tessellations and the k-means problem, as well as sort of questions in numerical linear algebra and spectral graph theory. So thank you again for attending, and Jin Chao, thank you for having me.
Thank you very much, John. Great talk, and the problem I don't actually know much about. I don't know, but it's very nice, very interesting. And is any question, John? Do you say?
I can have one. Like,
Uh-huh.
so I was looking at your error bound and so on.
Mhm.
Is there anything that you can say about the stability of this method with respect to the variation in terms of the weight matrix? Maybe you mentioned it, maybe I missed it.
Ah, I see. This is a good question. So you're asking questions about the stability of the embedding with respect to your inputted
Correct.
distances. This is a very good question. I can say that you, let me think for 20 seconds. I can say that as long as you don't have issues with vertices which are, let's say, data points which are very, very close to each other, but not the same, you have very good stability. The one caveat that I would mention is that if you have error of points that should be the same, but are not exactly the same, then this can lead to real issues. But if you have some sort of procedure that, let's say, puts points which are within some very, very small epsilon distance of each other at exactly the same place, like so small that they really should be the same, then what you have is something that is decently robust to small errors.
Okay. So here's one, from the chat. Quadratic functional here, for example, a strictly convex discrete. What is this? This is comment probably. Sorry. Okay, so there's one question here actually. What is the practical application you've been working on?
Okay. So for this work, I can say the typical practical application is, imagine you have some data set, let's say in a higher dimension, or some graph in a higher dimension, and you would like to try to visualize this in a lower dimensional space. So you have some high dimensional data and you want to get some sense for what does this look like. I can say that trying to visualize this in low dimensional space is quite important and is actually served as a pretty useful subroutine in other problems. So this can serve as a subroutine for, let's say, problems like k-means or other sort of like techniques to deal with data, because this often can remove, like, let's say, nonlinearities and things like this. But it's just quite useful for sort of data visualization. I would say that the stress minimization objective in particular has been especially popular in the 90s and 2000s, and to some extent in the 2010s. Recently, there's been a lot of sort of explosion of different types of techniques for data visualization for machine learning purposes. And so I would say the two modern things we look at, typically, I would say UMAP is the most recent as far as force-directed layouts go. And so trying to understand how these class of algorithms behave, I think, is quite important. And I think understanding what is a simpler objective function with still a lot not known about it is a very sort of important first step before dealing with, let's say, the more complicated objective function of, let's say, UMAP.
Okay.
Yeah, John, when you look at this objective function, you have this xi, the distance between xi and xj, the minus dij.
Mm-hmm.
I'm just having an naive question. Why don't you square that distance, then take the square, take the difference of the square?
Yeah, this is a perfectly reasonable question. So let me get
Would
to
that make life easier?
this place. Yeah. So you're asking, why don't we just use distance squared? Why don't we just look at the distance between squared? And this is a very reasonable question, because first of all, we do that, it now becomes an easy optimization problem.
Yeah.
And it becomes very nice. And I can tell you that, first of all, I'm not an expert on what constitutes a good looking drawing and what doesn't, but I can say that there's been many, many years of sort of experimental and aesthetic results in which have led sort of the community around this to more or less universally agree that you get the most representative drawings of your graph and the best drawings of your graph by this choice of weight of like 1 over d squared and looking at the distance between sort of the embedding and the actual graph distance squared rather than, let's say, the distance between them squared. So this is something that I can say is sort of slightly outside my purview, but the literature almost universally agrees that you get better things out of this algorithm, even though what you get is almost always a local minimum. It tends to be better for what you want than the global minimum that you get from the problem you just described.
I see.
Yeah, but no, that's a great and like that's a very natural question.
I thought the other one should be much easier.
Yeah, no, I mean that one, the minimization is is very, very easy. So.
And actually, the question was, I think John, you want to you separate the two different messages from Chris here. What happens to your results when you replace quadratic functional by e.g. strictly convex by the discrete LP norm, in particular as p goes to 1 or infinity?
So this is a good question, and this is something that has appeared in the literature. And what I can say off the top of my head is, first of all, when you go towards infinity norm, you're really getting something that is somehow very, very susceptible to sort of like errors or outliers. When you go to infinity norm, like outliers really control what's going on, and it's very likely that you're going to get something non-representative. Yeah. And so like imagine you have some, let's say you have some type of small world network or whatever it may be, you're going to have things which are not going to be at their exact distance to each other, but this gets overridden by the fact that you just want a majority of your vertices to be roughly the distance they want to be, because having everything at their right distance is not quite possible. And if you sort of weight this too much to the outliers, then this can lead to sort of very non-representative solutions. The one norm question is actually a sort of a very good approach, and this is slightly different. I generally try to think about that as somewhat of a difference of sort of preference, and my opinion is I don't feel qualified to sort of state, using 2 norm is better than using 1 norm, in the same way that I don't necessarily feel like a qualified person to state that, I prefer that like k-means is better than k-medians or like anything like this. I sort of put it in that type of category. But I think the 1 norm is a perfectly reasonable way to, is a reasonable thing to look at. And I believe it has been looked at.
So here's one question here. How does best looking graph correspond? Wait a second. Sorry, it's just being okay. How does best looking graph correspond with the often desired object in UMAP and TSNE, which is clustering classifications?
So you're saying I want to make sure I fully understand the question. And so I'll try to answer what I think the question is. I would say that I do think that, let's say, the sort of recent UMAP algorithm does have certain properties of it, which does make it sort of slightly more desirable than, let's say, heuristics for stress minimization. And I think that has been shown through things like clustering, which you mentioned, heuristically. But in terms of sort of being better, I think that's the best way you can describe it, is look at how this sort of like heuristically performs for different types of subroutines you want to do once you get your low dimensional Euclidean space. Because, okay, these are sort of like 2 inherently different objective functions, and these algorithms are just trying to do two inherently, different things. And so I would say focus on the specific thing you would like to do with your embedded graph is sort of like depends on, how strongly you should feel about UMAP versus stress minimization, let's say.
Great. I'm reading another question here. Can we use the method to merge multi-layer graphs?
So, sorry, there are sort of conflict. There are questions actually being addressed, I think, by Andrew Stewart on the site. So this is why I'm also a bit,
So what are you saying, John? John?
No, this question is actually not for John Urschel. I think those questions are currently being addressed by Andrew Stewart personally on the Q&A. So
Andrew's answering questions.
Yeah, he's answering questions on Q&A.
He did have a lot of overflowing questions, so I can completely understand that.
Yeah, that's what I'm sorry.
I'm not qualified to answer questions for Andrew. I can state that.
He was asking about graphs. I was just reading.
Yeah.
So any other questions you can find, John Harden?
Let me take a look.
I'm also trying to find, but
I didn't go through the Q&A where
so yeah, some of the open Q&A questions relate to Andrew's. I don't see any more from mine.
Yeah. Is this one related to you? Like why GCN performs so badly?
I don't GCN.
Okay, no. Then forget it. Then I have one for you then. How about, because you is that okay?
Yeah, of course.
So now this is sort of related to something that I'm more familiar with. If you work with the diffusion maps algorithm, which is one way to construct such a graph Laplacian approximation, then usually we have, an issue. I mean, at least in the numerical performances, we have the curse of dimension issue. If the intrinsic dimension, I mean, because we're interested to uncover low dimensional manifold, if the intrinsic dimension of this manifold is usually like around 4 or 5, then we are usually freak out in terms of numerics, because the error bound here is converging very slow with respect to the dimension. So there's a curse of dimension. So for this algorithm that you're talking about here, does that also applies, like, meaning?
This is a good question. I can say that here, the way in which I would relate this is that what you see when you have something which really does have some low dimensional structure is that you're going to see that your choice of dimension really affects how your sort of objective value behaves, and how this objective value changes over dimension really starts to tell you sort of like when you've sort of hit the right dimension that this should be in, if it has a low dimensional embedding. And so I would say that is something that I think is actually highly understudied for this type of problem, choosing the sort of correct choice of D, so that if you do have something which really does belong in a low dimensional space, it really recognizes this. And that's something that I think is quite understudied. For instance, there's a lot of literature around this for, other techniques. Like, okay, I keep going back to other things I know, but like, for instance, for k-means, how to choose your K is extremely, extremely sort of like well studied. But here, for instance, how to choose your dimension, I think, is not as well studied, although I think there's been some things. For diffusion mapping, it's sort of very straightforward. You just look at the sort of like how the energy behaves and when this sort of starts to drop off. But here, I think you just have to look at like how the objective function behaves in different dimensions.
Okay. At least for diffusion maps, there's a way how to measure D, like how to approximate D. There's many methods there, which may or may not be robust. So, okay.
Oh, with that note, maybe it's good time to wrap this one up. Thank you, John, so much for this beautiful talk and very interesting problems. And I also want to thank the other two speakers, Professor Dobbidges and Professor Stewart, for all these wonderful talks. And thanks everybody for the wonderful question. Okay, we're going to take a short break, 1 hour. We'll come back 2 p.m. and to go to the afternoon session, my Eastern time at least. Okay, thanks again. Goodbye, everybody. See you soon.